Welcome to massive open online course on fluidization engineering. Today the lecture will be on flow regime and its map, especially on gas solid fluidization. So, what is flow regime or pattern? Basically the multiphase flow behaviors that are affected by interfacial tension, weighting characteristics of the fluid on the channel wall, or you can say bed wall, and also contact angle and the exchange of mass, momentum and energy between the phases. And this flow regime dictates the flow behavior and shape of the interfaces between phases in a multi-phase mixture, which is commonly referred to as the flow regime, or sometimes it is called a flow pattern. What are the factors that affect on this flow regime? The flow regime of multiphase flow in a fluidized bed that depends on several factors like dynamic variables. What are the dynamic variables? Like what are the flow rates in the fluidized bed, flow rates of gas and liquid. Even if any other suppose phase like solid, if it is continuously flowing into the bed, then the solid velocity also will be one dynamic variables here. And geometric variables, of course, what should be the size of the bed, that is what is the diameter of the bed, what is the cross sectional area of the fluidized bed, and what is the particle diameter, what is the pore diameter of the distributor through which the fluid is distributed into the fluidized bed. And thermodynamic variables like what is the pressure inside the bed, how it can be changed, and or if I change the pressure inside the bed, then what should be the characteristics of the fluidized bed, and what should be the different hydrodynamic and transport processes inside the bed that depends on the pressure. And another thermodynamic variable, it is called temperature. Of course, temperature is the main effect here. Sometimes since the drying operation in the fluidized bed, you have to maintain certain temperature, and also if you increase the temperature or decrease the temperature, how this fluidization characteristics will change, that depends on the temperature variation. And other different transport processes like mass transfer, heat transfer, that depends on the variation of the temperature that is controlled in the fluidized bed. So, thermodynamic variables like pressure and temperature are the main important factors here. Physical properties, of course, any fluidized bed, whether it is gas solid or gas liquid and solid multiphase fluidized system, of course, the physical properties like density, surface tension and viscosity of the fluid medium, it will affect the fluidization characteristics. Like flow regimes, of course, if you change the properties of the fluid and also other dynamic, geometric and thermodynamic variables, then you will of course have the different type of flow regimes inside the bed. The boundary of the two regimes is sometimes referred as the flow regime transition. Of course, one regime to another regime, you will get to make change of one flow regime to another flow regime, what should be the barrier, what should be the point from which you can get the another flow regime, that point is called transition point, or the certain region, certain that is profile from that profile onward or beyond that point, you will get the different type of flow characteristics. So, the transition point, that is called flow regime transition. Okay, that also very important in this case. You have to know in which flow regimes actually this fluidization operation is being carried out. And different flow regimes, you will get the different behavior, different applications, different hydrodynamic characteristics, different mass transfer characteristics inside the bed. Now, See the diagram here in this bed, there are different types of flow regimes or flow pattern in gas solid fluidization system. Here initially you will see this is called fixed bed, that means here the solid particles are not being suspended at this gas velocity. So, here it is fixed bed operation. So, you cannot say this is the fluidized condition. So, this is just before the fluidization operation. After a certain change of gas velocity beyond this fixed bed operation, you will see there will be a change of characteristics of the fluid bed inside the fluidized bed. Like if you increase certain minimum gas velocity, then you will see this type of particulate, or you can say homogeneous fluidization operation. Here you will see there will be a significant change of the level of the bed. Here there will be some tilting, or you will see that wavy shape of the bed. That means, here beyond a certain minimum velocity of this fixed bed operation, you will see certain this fluid are going to be suspended here inside the bed. So, this is here one operation, this is called particulate regimes. So, whole this fluidization gas solid fluidization system you can divide it into two parts here, base operated and transport operated flow regimes. Now, base operated flow regimes, here you will see some flow regimes like homogeneous or particulate, you can say sometimes bubbling bed and also turbulent fluidized bed. And under this base operated system, you will see base operated fluidized bed, this bubbling fluidized bed, slugging fluidized bed, and also the turbulent fluidized bed will have different characteristics and different hydrodynamic characteristics. And also transport operated, here see fast fluidization and pneumatic transport. There are two types of fluidization flow regimes, and all these flow regimes will be changing if you just change the gas velocity inside the bed, but you cannot say that all these flow regimes will be changing only based on the gas velocity. No, if you fixed some gas velocity and if you change the other variables like geometric variables, if you like what is that particle diameter, if you change the what is that physical properties of the system, if you use different gas with higher density gas, then you will get different type of flow regimes also. So, let us see at a certain gas velocity here particulate bed, the characteristics of the particulate bed here the just particles are trying to suspended inside the bed, and there will be no bubble formation here. Whereas, in this case if you increase certain amount of gas velocity, you will see there will be a formation of certain gas, and there will be a certain shape of the bubble here. So, here gas will be distributed through a distributor, and from the distributor there will be a formation of bubble inside the bed. So, this type of phenomenon is called bubbling fluidized bed. And even if you increase little bit the gas velocity, this bubbling fluidized bed will behave and will form a bubble in such a way that the bigger bubbles will form, and those bubbles are going up through the center of the bubbles as a large bubbles, and this large bubbles sometimes it will be almost equal to the cross sectional area of the bed, that is diameter of this bed will be equals to the diameter of the bed. So, if it is diameter of the networks, you will see a slug you will form. Even sometimes you will see if it is not the same the diameter with the fluidized bed, then you can get the plug flow type fluidized bed here. So, there will be plug and slug. So, this is under the bubbling fluidizing condition. Even if you increase the fluid velocity, or you can say the gas velocity, there will be the turbulent condition will form. Here the bubbles will be forming, or you can say voids will be there, but that voids will not be exactly the bubble shape, and it will be sometimes longitudinal long bubble here, long bubble, and even in between these two bubbles there will be a channel of the solid particles or channel of the gas along with the solid particle in such a way that there will be a churning phenomena inside the bed. So, this is called churn turbulent fluidized bed. And slugging fluidized bed, you will see you will obtain very narrow tubes, narrow beds. In that case, slugging condition you can get, whereas the churn turbulent flow you cannot get in the narrow tubes. In that case, you have to have the diameter of the column at least 5 centimeter, otherwise it will be very difficult to get this churn turbulent, because this churn turbulent will actually follow, there will be internal circulation of the cell, internal circulation of the fluid particles and solids inside the bed, and there will be churning condition formation. So, this is the base operated, whereas in transport operated cases, if you increase further this gas velocity, you will see there will be a very dilute solid, that is concentration of the solid that distributed inside the bed in such a way that maximum portion will be the gap, or you can say the void inside the bed. So, here, but smaller particles also will be moving up, small amount of particles will be moving up, but this will be first fluidization and particles will try to move up as early as possible along with the gas. And in this case, of course, the fluidization condition will be far more than this minimum, that is settling velocity of these particles, or you can say terminal velocity of the particles. And pneumatic transport, here very dilute phase of solid particles, all the solid particles will try to go up, and it will be coming out from the top, and it will be again reused. Even for first fluidization also you can use or reuse these solid particles here. So, in pneumatic transport there will be no bubble formation, specifically shape of bubble formation will not be there, okay, and there will be a very dilute concentrated of solid particles, and it will be flowing up immediately. So, in this case at least 20 times larger than the terminal velocity of the fluidized bed inside the bed should be there. So, here you can get that from the fixed bed we can get different fluidization or different fluidized regimes like homogeneous, bubbling, churn turbulent, fast fluidization, pneumatic transport. Now, to get the minimum fluidization, of course, you have to maintain, maintain certain gas velocity, that is called incipient condition, and that incipient it is called incipient fluidized bed or minimum fluidization condition. So, of course, to get the fluidization, that minimum fluidization velocity should be required for. We will be discussing that how to calculate the minimum fluidization condition later on also. So, in this case we are getting the different fluidization, different fluidization regimes based on this solid and gaseous system. And you can get other different types of flow regimes if the fluidized bed is operated with liquid and solid, and also gas and liquid and solid. So, we will be discussing subsequent in lecture that what are the different types of flow regimes will be there in the fluidized bed. Now, let us discuss what should be the different characteristics of the different flow regimes in the fluidized bed. Now, homogeneous or particulate fluidization, this is as the gas velocity increases, the bed expands smoothly in a homogeneous manner. So, in this case you will see there will be a gap between two particles, very small gap between two particles through which the gas will be flowing upward without making any bubble inside the bed, or without making any churning condition, without making any dilute phase, without making any other slug condition. You will get the simply homogeneous flow inside the bed. So, this will be happening in a condition which is called homogeneous fluidized bed. The top surface of the fluid bed is well defined with small scale motion of the solid particles. Here, of course, the this minimum fluidization condition, you will see the top surface of the fluid bed will be well defined, and it will behave like a liquid here. If in this case the surface of the bed of course will be tilting, or it may change according to the operation. And then also it will be well defined, and there will be a little bit motion of the solid particles at this homogeneous fluidization regime. The solid particles have little tendency to aggregate also. In this case, there will be no actually formation of agglomerate inside the bed, and throughout the cross section you will see there will be a uniform distribution of the gas through the space between the solid particles, that is called voids in the bed. And further increase of gas velocity, bubbles are formed in this case. In this particulate fluidized bed, with the same particle, you will see if you just change the gas velocity little bit higher, and you will get this there will be a change, there will be a change of phenomena from this particulate to the bubbling phenomena. Inside the bed there will be a formation of small amount of bubble, okay, small bubbles, and it will be going upward at that certain velocity. And the particulate fluidization occurs in the range of gas velocity that will be of course that will be higher than the minimum fluidization velocity, but it should be less than the fluidization condition of the bubbling fluidized bed. So, here UMF here denoted this minimum fluidization velocity, and UMB is the minimum fluidization velocity for bubbling condition. So, in this case you will see this particulate bed fluidized regimes can be defined only when the fluidized bed is operated within this minimum fluidization to this bubbling fluidization condition, and this pattern is sometimes called as homogeneous fluidized pattern. So, this is the characteristics of the homogeneous or particulate fluidization. Whereas, bubbling fluidization, of course, you have to increase the gas flow rate beyond this particulate fluidized bed, so that you can have large instabilities or some instabilities in such way that there will be a formation of bubbles and channeling of the gas that will follow inside the bed. And higher flow rates, of course, the movement of the solids becomes more vigorous in that bubbling condition, and in this bubbling fluidization condition, whenever bubbles will move up, there of course the bubbles will carry some solid particles from its behind by making wake. So, and also from the top there will be a there the bubbles will move aside that solid particles from its top portion, and whenever bubbles will move up at the surface, it will be collapse, and solid particles will be throwing out at the surface. So, this type of phenomena will happen inside the bubbling fluidized bed. So, there will be some bubbles will form, and those bubbles will be forming from the distributor region. The bubbles will be very smaller, and whenever it will come to the top, you will see the bubbles will coalesce to each other, and it will make big bubbles, and after coalescence, and then it will go up very fastly. So, initially bubbles will move slowly because its size is very small in near about the distributor. It depends on the whole diameter of the distributor, and the size of the bubbles depends on the whole diameter of the distributor, and because of which you will get the bubble size very small, but whenever it will move up due to the coalescence of 2 or 3 bubbles at a time, there will be a formation of big bubbles, and it will go up very fastly because of their buoyancy effect. So, bubble size increases as gas velocity increases. Of course, you will get the different sizes bubbles as a function of gas velocity. If the bubbles become larger, the phenomena of slug is also developed. So, of course, if you are making a high gas velocity, then you will see the 2 bubbles will come to each other and making a big bubbles, and these if these big bubbles are almost equals to the diameter of the bed, then it will make one slug. Even plug also it will be there, because the sometimes two bubbles, whenever it will be coalescing making a big bubble, it may be approximately 85% of the cross diameter of the bubble, then it will go up, but it will be very large, and as a slug, that means as a plug it will be moving up. So, it will be plug flow. And slugging, the gas bubbles are buoyed coalescence and grow as they rise. So, in that case it will be forming a slugging fluidization. In a small diameter deep bed, you will see the bubbles may become large enough to spread across the bed. So, in that case you will see the slugging tendency will be there in the bed. And if the bubbles are actually vertically elongated and move axially and move axially, the phenomena sometimes it is called axial slugging. So, there are two types of slugging will be there, flat and axial slugging. So, if most of the bed cross section is captured by the bubble or void, the phenomena is called flat slugging. So, that is why there if axial slugging means there of course, the bubbles are vertically elongated, whereas the flat slugging the bubbles will be horizontally elongated, and it will occupy most of the cross section of the bed. Whereas, turbulent fluidization, in this case small bubbles or void are formed. So, the solid particles of course clusters and it will move rapidly by forming elongated or you can say that forming elongated bundle of slugs. So, the in this case you will see some clusters of particles will be forming, and that clusters will move upward, and sometimes these clusters, whenever it will be collapsing or it will be just reaching to the bottom of another slug, it may be elongated and bundle of slugs will form. And the top surface of the bed in this flow pattern, of course, it is very difficult to distinguish, because you will see there will be the unstable condition of this turbulent fluidization, and at the same time solid and gas both will be flowing in such a way that the particle and gas, that is particle fluid interaction will be more higher, and because of which that you will not get the particular shape of the surface inside the bed, and it will be very unstable in this case. The turbulent fluidization pattern, it will start when bubble coalescence and breakup reach a dynamic balance. Of course, there will be a simultaneous happening of coalescence and breakup of the bubble inside the bed during this turbulent fluidization. So, for smooth bubbling condition, the smooth coalescence, but breakup will be less, whereas in the turbulent condition, because there are what is that intermixing and also the internal circulation of the fluid that will sometimes disturb the uniform movement of the bubbles, and it may break the bubbles, and also bubble interaction will grow up, and also coalescence also because of that it will be there. So, simultaneous operation, simultaneous actually process of coalescence and breakup will be there inside this turbulent fluidization. And in a fluidized bed with increasing gas flow, in this case most unstable condition will occur, and of course, this corresponds both the beginning of the transition of bubbling and slugging to turbulent fluidization and to bubbles of maximum size here. And first fluidization, in this case particles are transported out the top. Of course, the gas velocity will be so high, at least 20 times of the terminal velocity of the particles there. So, if 20 times of the terminal velocity of the gas, you will see particles will not be coming back to its original position, and it will move up and it will be transported out the top, and that transported out solid, of course, it will be separated from the gas mixture by some what is that separator, and after that it will be again used for this fluidization. So, in this case particles are transported by the gas here. Here back mixing of the solid particles will be less because high kinetic energy here. And in this case you will see the must be replaced by this by the adding solids at or near the bottom of the bed. Of course, you have to add the solids here near the bottom of the bed, otherwise if you cannot actually add the solids at the certain height, because at this operating condition if you supply from a certain height of the bed, it will go immediately to the top and it will not having that much of retention time inside the bed. And the clusters of the particles move of course downward near the wall, while gas containing dispersed particles moves upward in the interior. Of course, it will be there if you are using very fine particles, there will be a chance to form of clusters, or you can say agglomeration, and different sizes of clusters will be there inside the bed. That depends on the gas velocity and also the weightness of the solid particles there. And if there are big size of the clusters are formed inside the bed, of course, it will not be reaching immediately to this top. Sometimes because of this weight, it may go back to its previous position. That means, there will be a tendency of formation of circulation to its downward, and that is why the downward movement of the solid particles near the wall, because to get back to it will have enough space. If for the very narrow tube, you may not get this type of back movement or downward movement of the solid particles inside the bed. So, to get this backward, that means downward movement of the solids, there will be a large diameter of the fluidized bed. And the solids in the first fluidized bed may typically occupy up to 25% of the bed volume, and is in a state of extreme turbulence marked by extensive refluxing of dense strands and packets of particles there. So, here it is very important point to note that in the first fluidized bed occupy up to 25% of the bed. So, otherwise it is very difficult to get this type of first fluidization condition. Now, pneumatic conveying fluidization, in this case homogeneous dilute phase of the solid fluid are observed. In this case, there will be no bubble formation, there will be no what is that churning condition, there will be no what is that first fluidization condition here. Only the solid particles will straight forward going up and it will be coming out from the top of the bed. The particles are fully suspended in the gas, and particles travel like a piston with relatively high pressure drop and high feed rate of particles here. So, there will be, you will see there will be a velocity of the solid, or you can say that some flow rate of the solids along whatever the gas velocity have. Of course, in this case also more than 20 times of terminal velocity of the solids or the fluidized bed will be operated here. Now, all particles fed in the transported, all particles that is fed in the bed, that will be transported out the top of the bed as a lean phase here. So, in this case this pneumatic conveying fluidization, of course, it will depend on the velocity and the solid content of the air flow, and different transport states may occur in this case. And there will be there will be different transport states like suspension flow or dilute phase transport, intermediate flow or you can say strand transport, and dense phase dilute or you can say dune transport phase here, and also dense phase plug transport of course will be there as per figure it is there. So, here this will be your suspension flow or dilute phase transport, and this is B here intermediate flow or strand transport. Here you will see this how the solid particles are moving. Here flow pattern in each section will be almost same here, whereas in the C, that is called dune transport, here in this case the flow pattern will not be same. In the middle section maybe, or that depending on the gas velocity and solid particles type, it depends on the also cross sectional area of the bed, that how the solid particles will be transporting here. And also D is called plug flow. Here some plug or bubble formation will be there inside the bed. There will be dense portion will be formed here inside the pneumatic conveying fluidized bed. So, this happens because this cross sectional area of the fluidized bed. And suspension flow or dilute phase transport at high velocity, the solid particles move through the line distributed uniformly across the cross section. Of course, the particles impact against each other or against the bed wall will be there. And intermediate flow or strand transport, if the velocity is reduced while the solid content remains constant, you will see the energy of the flow that will not be sufficient to hold the entire solid mass that is suspended in the bed. But some of the solid particles you will see slide along the bottom of the pipe in the form of strands, and the rest are transported in a suspension above the strands. Whereas dense phase dune transport, if the velocity is reduced further, you will see the solid particles move like a dune, and particles are moved over the summit of the dune and are deposited on its sheltered side. If the velocity is reduced further, incipient plugs may be formed from the dunes which occupy a major part of the cross section of the bed. And dense phase plug transport, in this case a very low velocity, the material occupies the entire cross section of the pipe and plugs are formed, and plugs advance slowly if the air compressor does not have sufficient pressure. Of course, plug transport may quickly lead to blockage of the pipeline. So, this will of course, this design of course will be having the beyond this 20 times of the terminal velocity of the solid particles. And then spouted fluidization, this is another important fluidization regime here. This pattern represents a mode wherein comparatively coarse uniformly sized solids are contacted by gas. In this case, you will see that solid size or particle size will be little bit higher than the other particle. So, in this flow pattern, gas forms a single opening through the distributor, and in which the some particles flow and fall to the outside. At higher gas flow rate, you will see agitation becomes more violent, and the movement of the solids becomes more vigorous, and the bed does not expand much beyond its volume at minimum fluidization. Now, in this case you will see principal features of flow regimes here. So, we are getting different flow regimes like fixed bed here, that is before fluidization, particulate regimes, there will be some region, that is you range the velocity, that is UMF is minimum fluidization velocity, UMB the bubbling fluidization, this is for minimum bubbling fluidization condition. In this case, bed expands smoothly in a homogeneous manner, top surface well defined, the small scale particle motion will be there, whereas bubbling regimes in this case beyond this minimum bubbling fluidization velocity, whereas the less than the minimum velocity for slugging condition. In this case, gas voids form near distributor, the bubbles will coalesce and grow, rise to surface and break through. Whereas slug flow, bubble size approaches column cross section, top surface rises and collapse with regular frequency here. And the turbulent fluidization flow regime, in this case of course, you will see pressure fluctuation gradually decrease until turbulent fluidization flow regime is reached. And turbulent regime, small gas voids and particle clusters dart to and fro, top surface is very difficult to identify. And fast fluidization, no upper surface to bed and particles transported out the top in clusters and must be replaced there. And pneumatic conveying, in this case no bed, of course, you will see that particular bed, that will be some label, it will not being having in their the pneumatic conveying. All particles fed in are transported out the top as a lean phase there. Now, let us classify this different fluidization condition as per fluidization regime, and also based on the classification of the particle. Now, I think we have discussed in previous or earlier lecture, there are 4 different types of gilded particles like C, A, B and D. Now, you will see if we consider the C particles and if we increase the gas velocity, then how what type of fluidization regime you can expect in your fluidized bed. Suppose here this particle type is C type, that means very cohesive in nature, very fine particles here, interparticle attraction is very high, and there will be a cohesiveness nature, because of which you may expect in the fluidized bed as this channeling, and also you can have the flow regime of turbulent churning fluidization with this fine particles, and also you can get the fast fluidization, of course, if the gas velocity, if it is greater than 20 times of terminal velocity, and you can get the pneumatic transport which will be of course greater than 20 times of terminal velocity of the particles here. So, this C type with this C type particles you may expect this channeling, turbulent churning, fast fluidization, pneumatic transport. Whereas, A type particle, the particle size is little bit higher than this cohesiveness that we have earlier discussed, that greater than 100 micrometer. In this case, you can get the smooth fluidization, bubbling fluidization, whereas in C type particles you may not get the bubbling fluidization. In this A type fluidization you can get the bubbling fluidization here. The you can get the turbulent churn turbulent fluidization and also fast fluidization, but it is very difficult to get the pneumatic transport with these particles. So, so all these flow regimes you get only by increasing the gas velocity with fixing this solid particles type. Whereas, with B type particles, in this case you get bubbling fluidization and turbulent fluidization, but you cannot get this what is the smooth channeling, fast fluidization or pneumatic transport type fluidization with these B type particles, because here the size is higher, this size matters. So, but D type particles, here only 2 types of fluidization you may expect here, bubbling fluidization and turbulent churn turbulent fluidization. You cannot get any smooth channeling, fast or pneumatic transport fluidization. So, only the D type particles applicable to get this turbulent and the bubbling fluidization. So, it is very difficult to get this other type of fluidization by choosing one particle type, but you can infer what type of fluidization regime can get from this, can be obtained from this particle, from this knowledge. Now, flow regime map and its transition, very important here. Grace 1986 he has done lot of experiment with different type of particles and with varying gas velocity in wide range. Of course, with air they got different results of different fluidization phenomena, and they have actually suggested one map by representing the transition of different flow regime based on their experimental data. And they have represented the transition of different flow regime or different patterns, flow patterns inside the fluidized bed by just choosing choosing the axis in different way to represent it graphically. In this case, you see this here flow regimes. In this case, very important. In this case, you will see the x axis is dp star. dp star is what is that? Non-dimensional particle diameter, which has been suggested in this way. This will be dp into that means here rho g into rho s minus rho g by mu square into g to the power 1 by 3, or you can say dp star is equal to Archimedes number to the power 1 by 3. Whereas, this y axis, that is u star is the non-dimensional velocity of the gas which is defined by Re by Reynolds number, that is Reynolds number by Archimedes number to the power 1 by 3. Now, if you see this figure here, we are getting different type of phenomena here. First, we will see this C, A, B and D. These are the different type of particles here, and these lines, this is the lines, these lines form lines will be representing the transition line, or the data on this line will give you the transition data from beyond which you can get the what is that different flow pattern. Here C, here very interesting here is that here if you consider the C, here C, in this case you will see some flow pattern map here. This is called, this region is called, this is spouted bed, this is bubbling fluidized bed, this region is bubbling fluidized bed, and here pneumatic transport fluidized bed, and this region is called fast fluidization bed. So, here see here if we consider C particles, this is the C particles C regime. What happened if you consider the C particle here, or the point, any point at this point, if you go, you will see at this location what is this flow regime here. This is the point where you can get at this point, like suppose 1 dp star is equal to 1, dp star is equal to 1. If you go up here, you can get this this one, this here, this is your minimum fluidization condition, this is your minimum fluidization condition, and this is your terminal velocity profile, and at this point. So, with this one dp star you can get one terminal velocity, and here if you go this, and if suppose u star is somewhere here 1, what will happen, this is the beginning of the first fluidization condition, and then beyond which after this, suppose up to 10 here you will see at this location you can get the first that is pneumatic transport condition. Now, if you consider the B particle here, and if you consider that dp star is equal to this, like what is the value here, like suppose 10, then it is 11, then dp star is equal to 11, what will happen, you can get up to this here, any point here, whether it will be spouted or some other, that you can obviously you can take from this regime, that it will be the spouted region here, because here in this case at this any location you just any point here G, by this combination of this point you can get here spouted. Even if you consider here, suppose this is what that, this is dp star is equal to suppose 11, and you can get this bubbling fluidization only when the u star is equal to 1. So, this is the phenomena. So, from this graph you can read actually, or before going to the experiment you can have some rough idea from this flow pattern map, whether you are getting the bubbling fluidized bed or not, or you are getting slugging condition, or you are getting pneumatic condition, or you are getting spouted beds, that you can of course have some idea from this flow regime. Any before going to start any experiment, you can of course suppose you want to have the bubbling fluidization condition, then what you have to do, you have to select B type particle first. Select B type particles. So, if I select the B type particle, and if you want to operate it at 1 point, what is this? This is okay. This is the dp star is equal to 10. Then you have to have the velocity, at least minimum velocity should be here at this point. So, this is your point from which you can get with this B particle what should be the velocity of the gas by which you can get the bubbling fluidization condition. And other also, if you want to get the spouted beds, like you have the PD whose type is D type, where dp star is equal to this, and then you want to get the spouted bed, suppose want to get this spouted bed at this bubble, and what should be the velocity from which you can calculate, this will be your velocity by which you can get the spouted bed. So, in this way, before going to start your experiment, and if you want to apply this fluidization operation for specific operation, and if you know that the operation will be favorable in bubbling condition, then the operation condition you can select from this fluidization map also. Other type of fluidization regime, here you can say here some Bass operated, here B and Grace 1995 they have given this fluidization map. Here Bass operated and transport operated, two types of fluidization map they have presented here, and these are the lines you can get the transition points, and also here this is the transition point, these are the transition points or transition line here beyond which you can get the fluidization operation, whereas below this line or less than this point you can get the packed bed at a different boundary of the particles here. Now, this in x axis it is represented by Archimedes number to the power 1 by 3, and here y axis is u star here this is defined as Reynolds number by Archimedes number to the power 1 by 3, and dp star is the Archimedes number to the power 1 by 3. Here again this at this suppose here type A and C, this is mixture of particle A and C, and if you go this here in this region you can get this some minimum fluidization or particulate fluidization, and beyond which at this location, these are the locations in which you can get the bubbling fluidization. This location means at any point you select and you read the data of this AR and U star, and from which you can have the idea what should be the value of gas velocity and what should be the value of Archimedes number, from which you can get what should be the diameter of the size, if you know the all other parameters constant here. And also the turbulent fluidization, this is here also, this is the transition line beyond which you can get the turbulent transportation, and also below this point you can get the turbulent fluidization. So, these are the transition points, these are the transition points, these are the transition points. So, these are the transition points, and the data with these transition points they have developed, they have suggested some correlations from which you can get the transition data. That means at that particular value you can get either this packed bed or suppose particulate bed, that depends on the operating condition and other different variables of course. Suppose to get the pneumatic condition, so in that case what should be the minimum velocity you can get from this correlation, what should be the minimum velocity to be maintained, so that you can get the pneumatic transport condition here. So, in this case you can from these correlations, these are the correlations that is been developed from this experimental data, from which you can get the minimum fluidization condition. So, we will be discussing what should be the minimum fluidization condition, and the different flow regime transition we will be discussing later on also. And here of course, you will see one term is there UC. UC is a very interesting point. This UC corresponds to the point where the standard deviation of differential pressure fluctuation reaches a maximum. In the fluidized bed, you will see whenever it is operated under a certain operating condition, the fluctuation of the pressure inside the bed of course will be there. Now, this pressure, from this pressure fluctuation you can also obtain what type of flow regimes there in the bed. Generally, the standard deviation of differential pressure fluctuation, when it will be reaching a maximum, you may expect there will be a choking, that is called pneumatic transport there. And the critical velocity, that is SE, which is defined as the point where the solids begin to be entrained significantly inside the bed at this particular fluidization operation, then it will be called as AC. That means, here the significant entrainment will be occurring. Now, this very important, but whenever you are considering, you are working with transport operated fluidized bed, you have to consider the fluidization velocity as a V, which will be of course the beyond the minimum fluidization, and you have to add this minimum fluidization along with the operating fluidization condition there. And another important point, that bubbling fluidization, how you can get, when exactly at which velocity you can get, or you can expect the bubbling fluidization there. You can get the minimum fluidization velocity for bubbling condition by this correlation here. See here, see 33 into dP into rho g by mu g to the power 0.1. What does it signify? It signifies that if a particular dP, if you are just keeping it constant, and if you increase the density of the gas, you will see the bubble velocity. That means, here the velocity of the gas inside the bed will be so higher that you can get the operation of the bubbling fluidization. But what should be the minimum? You just, if you consider that air and particle size is 100 micrometer, and here if you substitute here the dP is equal to 100 micron, that is you have to convert it to the meter, and then if you substitute here rho g, that is 1.2, and by mu g, mu means here what should be the viscosity of the water, viscosity of the air here. So, in this case viscosity of the air 0.00018. So, if you substitute, you will get the minimum bubbling condition. So, you can directly apply to get the minimum bubbling condition this range here. So, you can easily calculate before starting the bubbling fluidization condition operation. Another important fluidization map or fluoregime map here given in different way. That means, here in the x axis you will see this is the CD into Reynolds number to the square whole to the power 1 by 3. This is one parameter, and also here another parameter R E into CD to the power 1 by 3. What is CD? CD is nothing but the drag coefficient. It will be discussed later on, also even previous earlier class also what is drag coefficient has been discussed. So, this drag coefficient. So, here in x axis you will see for different particles here group C, even mixture of group A and C, group A and group B and group D, Geltert group D particles. For this type of particles you will see different flow regime, different flow pattern you can get by this axis. Here these are the dotted lines are represented by the locus of UMF. That means, at this point you can get the minimum fluidization to from what is that packed bed to the particulate fluidized bed. Whereas this line will give you the terminal velocity of the particles here. Now, if we consider any group C particles here, C at this what is that, if the value of this x axis, this x is equal to this, then and here y is equal to this, then you will get this value for a particular x is equal to 1, and then here what should be the value of what will be the flow regime you may expect here. So, this regime is nothing but see locus of UTR transition, that means for transport flow regime. So, here at this location you can get transport regime, whereas in this position you can get the turbulent fluidization condition, and with this y value of this you can get the what is that bubbling and bubbling fluidization condition and slugging fluidization condition also. So, this is one way to represent the different flow regime map here. Now, what should be the transition from particulate to the bubbling fluidized bed? The equation here it is given, that is developed by Geltert and Abraham. So, to get the minimum bubbling fluidization velocity you can use this correlation to calculate for minimum bubbling fluidization condition. For minimum bubbling velocity also there are another correlations, it is important from which you can calculate the minimum bubbling fluidization condition. Here in this case this is a function of density of the gas, viscosity, particle diameter, solid density, and also there will be a what is that fraction of powder which has the particle diameter is 45 micrometer. Generally for FCC catalyst of size 5 to 100 micron at gas velocity UG is equal to 3 UMF, bubbles begins to form here. In group A powders, when UMB, that means minimum bubbling condition is greater than minimum fluidization, are constantly splitting and coalescing and maximum stable bubble size is achieved. This makes good quality smooth fluidization here. And also through splitting and coalescence of course, the bubbles achieve maximum stable size and it will be effectively independent of gas velocity or vessel size. Non-bubbling expansion of a fluidized bed of group A powder as the gas velocity is gradually increased there. A transition from bubbly to slugging fluidization, of course, here is the minimum fluidization condition for slugging is UMF is equal to 0.07 into GD to the power 0.5. From this correlation you can get what should be the minimum velocity for slugging condition, and the minimum velocity you can calculate from this equation. And other criteria for slugging also here it is seen that there are several other criteria to get the slugging fluidization here. If velocity, terminal velocity is by GDP, that means it is called Proud number. If it is greater than 140, then you will see there will be a stability of upward flow of a uniform unbounded suspension you can expect here. No allowance for Wolff effects will be there. If this Proud number is greater than 0.35, of course, you will see there will be a slug stability based on the equation of here Harrison et al. They have produced here. and this criteria will give you the slug stability based on the empirical evidence, and these correlations here, these correlations will give you the slugs postulated not to be able to rise faster than porosity waves. Of course, these correlations has been developed by Smith 1978, whereas Goetz and Carblow 1981 they have observed or some mechanism of slug stability based on the modified Harrison equation, and they have developed one criteria for which you can get the slugging condition based on bubble splitting from the rear wall. So, these are the criteria, other criteria from which you can expect the different slugging condition. Now, this slugging transition you come, this is the condition from which you can get the slugging transition. And if the bed is deeper than this critical height, then the slugging will occur when the gas velocity exceeds UMS given by the equation B here. This is your minimum height of the fluidized bed. Now, if the bed is deeper than this critical height, then slugging will occur, then the gas velocity exceeds UMS given by this equation, and slugging will not occur provided the criteria in equation A is satisfied. This criteria works well for most powders, and this is the condition from condition or transition of slugging to Chern turbulent condition, and from this transition you can expect what type of either the slugging or turbulent, or from slugging to turbulent how can I get to operate. And this is your transition from Chern turbulent to fast fluidization, of course, and by this equation you can calculate to get the minimum Chern turbulent flow or just to start the fast fluidization. And a transition for pneumatic transport fluidization, of course, at a fixed solid flux, the transport operated fluidized bed experiences bubbly, slug flow, turbulent flow or fast fluidization before achieving pneumatic transport. Now, according to B and Grace 1995, you will see a bubble free dense phase flow regime may also exist for group A particles. So, in such cases the flow patterns of the transport line are completely determined by the relative velocity between the gas and the particles phase rather than the superficial gas velocity. The minimum fluidization velocity under this condition, of course, denoted by VMF, all other velocity under continuous condition are represented by capital here letter V instead of small letter u used for base operated fluidized bed can be estimated. And the minimum fluidization for pneumatic transport condition you can get from this equation here. Pneumatic transport condition here, minimum pneumatic bubbling condition here, this is your minimum pneumatic transport bubbling fluidization and minimum pneumatic slugging condition also here. So, this is the case transition for pneumatic transport fluidization from which you can get this type of equation from which you can calculate what should be the choking velocity in the pneumatic transport condition. What is choking? Choking actually is generally used for to describe a phenomena which occurs when there is an abrupt change in the behavior of a gas solid conveying system. The choking point therefore has been characterized by the formation of slugs or plugs, or there will be is there any severe instability or not. Three types of choking generally are observed in fluidization operation: accumulative choking, classical choking, blue arrow strand pipe induced choking. So, different chokings will give you the different phenomena, and there are various definitions of the choking that observed in the fluidized bed that are observed. And here classical choking, of course, you can get the apparent relative velocity at choking that can be calculated by this equation here. Transition from homogeneous to dilute to core annular, this is very important correlations you can directly get from homogeneous to the annular dilute flow by this equation. Only thing is that you have to change the solid flux here, and also you can change the diameter of the pipe. If you change, then you can get the annular condition of the fluidization. So, next class onward we will be discussing some other part of the fluidized bed like implication of what will be the ratio of this minimum fluidization to minimum bubbling condition, how it will be affecting that. Okay. Thank you.